Hi everyone, my name is Carlisa Priandana. I'm from the Department of Computer Science, IPB University, and you can call me Lisa. Today I will present about our research entitled The Development of Autonomous UAV Quadcopters using Pixhawk controller and its flight data acquisition. Okay, this is the outline of my presentation. So I will start with the introduction and then move on to the methodology, then continue to the autonomous quadcopter development, results and discussions, and finally the conclusion. Yep, this is the first part of my presentation, the introduction. As we all know, unmanned aerial vehicle or UAV of type quadcopter is a copter with 4 driving motors, as you can see from this picture here. It is widely used in various applications, including in agriculture. However, currently, the widely sold quadcopters in the Indonesian market are those that are controlled manually using remote control. And that is why we want to try to develop 2 autonomous quadcopters. First is of type F450 with a diagonal dimension of 45 centimeters, and the second is the F330 with a diagonal dimension of 33 centimeters. Sorry, I will move this picture a bit to the top so you can see. Yep, this is it. This is the second quadcopter. Okay, the aim of this research is basically to support various quadcopter applications on fixed agricultural lands. So we assume that the land is already fixed and we can generate any trajectory, and the quadcopter is expected to be able to fly autonomously following the determined trajectories. Here in this research, we use 2 predetermined trajectories, which is the rectangular and circular trajectories. Now, the second part of my presentation is the methodology. So what we do is first we assemble the quadcopter components and then we test the functionality of each component. If all the components can function properly, we move on to the system configuration and calibration. If this is successful, we move on to the generation of automatic flight route, the circular and the rectangular type. And then we fly the quadcopter autonomously following the generated routes. Then we record the flying data, and then we end the research with evaluation and determination of future works. Let's move on to the third part, the autonomous quadcopter development. First, I will explain about the components of the 2 developed quadcopters. So the 2 quadcopters is basically the same, only different on the size of the quadcopter. So the first quadcopter here used the F450 frame because the size is 45 centimeters, and the second quadcopter used the F330 frame, which has the size of 33 centimeters diagonally. Both quadcopters use the same flight controller. Both quadcopters also use the same battery and also the same wireless telemetry, which is used for flight data acquisition. Other than that, the quadcopter use different GPS sensors, different radio controls, and different motors and propellers, and therefore also different electronic speed controller. Okay, this is the block diagram of the 2 developed quadcopters. Both quadcopters use the same controller, which is the Pixhawk radio link controller. Inside the Pixhawk controller, there is already an inertial measurement unit, which consists of various sensors in it, magnetometer, for example, barometer, gyroscope, and accelerometer. And then other than these sensors, we also add the GPS sensors. And then we add safety switch and buzzer for safety reason. And then we attach the electronic speed controller to the Pixhawk controller to control the motor. Okay, this is the trajectories that we designed. This is the rectangular trajectories and this is the circular trajectories. As you can see, we designed 4 waypoints for the rectangular trajectory and 37 waypoints for the circular trajectory. And then we try to test the 2 quadcopters following to fly autonomously following these 2 trajectories. Therefore, we have 4 testing scenarios. First is the F450 quadcopter following the rectangular trajectory. Second is this quadcopter using this trajectory. The third one is the F330 quadcopter to fly autonomously following the rectangular trajectory. And the fourth one is the F330 quadcopter to fly autonomously following the circular trajectory. So we have 4 testing scenarios. Yeah, and the result is as follows. So we basically just compare the real trajectory of each quadcopter to the desired trajectory or the waypoints that we have defined. And we use the mean square error for the qualitative data. And this is basically the overall results of our test. So the first flight test is quadcopter F450 with rectangular trajectory. You can see the results from this figure here. The dots shows the waypoint path and the lines shows the real trajectory of the quadcopter. And you can see that the quadcopter can follow the waypoints successfully with acceptable error value, as you can see here. Yeah? This is the mean square error value. And for the second test, this is the waypoints. Yeah, the dots shows the waypoints, and the real trajectory of the quadcopter is the line. You can see that the quadcopter can also follow the circular waypoints, circular trajectory with acceptable error, as you can read on this table here. And then the third flight test is the rectangular trajectory, but for the second quadcopter of type F330, you can see again here, the waypoint is the dots here, and the real flight of quadcopter is the lines here. And you can see that the lines can follow the dots with acceptable errors, especially on the corner of each dots. Yeah, this is because the quadcopter cannot turn like this, but it has to have a radius to turn. Yeah. Okay, and the fourth or last flight test is the quadcopter F330 with circular trajectory. And you can see that this second quadcopter can also follow the circular trajectory with reasonable errors here. Again, this is due to the limitation of the turning radius of the quadcopter. Okay, because all the 2 quadcopters can fly autonomously following the desired trajectory with reasonable error, we also take the flight data from all the sensors. We have data from attitude, roll pitch yaw. We have data control throttle and altitude information or data. We also have the data from the GPS system. We have the GPS accuracy data as well. And then we have the data from the EMU sensors. We have data from magnetometer and also data from RC output. You can ask for this data, and if you need this data for your research, for example, you can just contact me, Lisa, through this email, and I will give you the access to the data. Okay, as a conclusion, we have successfully developed 2 autonomous UAV quadcopters of type F450 and F330, and both quadcopters can fly autonomously by following rectangular and circular trajectories with acceptable errors. As a future work, we want to implement these 2 autonomous quadcopters to some specific agricultural tasks, such as the surveillance, fertilizing, and pest control tasks. To do this, we need to add some hardwares, including camera and actuators, depends on the defined task. And we will also do the image processing to be implemented in the agricultural surveillance task. As a remark from this research is we already produced some quadcopters flight data from various sensors in the quadcopter, and this data is expected to be able to represent all the quadcopter's attitudes during its flight, such as the takeoff, hover and landing, and these data are available to be used for further research on quadcopter movement. So if you need this data, once again, you can contact me or the other authors, and we can share the flight data of the UAV with you. So this is the end of my presentation. Thank you very much for your kind attention. This is my email address once again. Thank you.